You open Zepto and tap dairy. 50 items appear, each with an in-stock or out-of-stock badge that happened in under 2 milliseconds. 0 SQL queries were fired, 0 table scans. Behind every one of those badges is a hash map lookup in Redis. In 8 minutes, you will understand exactly why an array cannot do this and how a hash map makes it trivially fast. 4 things why arrays fail for Zepto's inventory lookup. How a hash map gives O1 access. Zepto's exact Redis implementation and the interview pattern for when to reach for a hash map. Customer opens dairy, request hits the API gateway. Order service needs to check if SKU ID 4521 is in stock at store 17. With a plain array, the inventory list is stored in index order SKU0, SKU1, SKU2. To find SKU4521, the service scans from position 0. That is, ON Zepto has 10,000 SKUs per dark store. With 50 concurrent users, that is 500,000 comparisons per second, just for browsing. The API gateway routes the request to the order service. The order service holds the inventory array in memory, 10,000 entries. It loops from index 0 until it finds SKU4521. That is linear time. Every lookup is a full scan. Add 50 concurrent users and you have 500,000 comparisons per second before a single order is placed. Worse, the array lives in PostgreSQL. Each scan fires a full table read. At 10 million daily orders, checkout alone generates 100,000 inventory reads per second. SQL cannot handle this. The array approach collapses at Zepto scale before you even add caching. Hash map. 3 operations: insert, lookup, delete, all amortized O1. The hash function converts any key to an integer bucket index in constant time. To look up SKU4521, you hash the key and jump directly to its bucket. No scan, no comparison loop, just one memory access. Collision handling with chaining keeps worst case manageable as long as the load factor stays below 0.75. The trade-off is space. Hash maps need ON extra memory to store the hash table. At Zepto, 400 dark stores times 10,000 SKUs equals 4 million keys. Each key is roughly 30 bytes, total 120 megabytes in Redis. For a system that processes 10 million orders a day, 120 megabytes of RAM is trivial. Speed wins. Zepto stores inventory in Redis as a hash. The key is inventory. Store ID, SKU ID. The value is an integer. The current stock count. HSET writes a field. HGET reads it. HDEL removes it. HINCRBY decrements atomically. That is the decrement operation on checkout. Customer taps checkout. The app sends a post request to the API gateway. The gateway checks the auth token and rate limit both pass. The request is forwarded to the order service. The order service fires HGET inventory 174521. Redis returns 42 in under 2 milliseconds. If count is greater than 0, the order proceeds. HINCRBY decrements the count atomically. Concurrent orders cannot cause negative stock. Cache aside, on a miss, fall back to PostgreSQL and repopulate Redis. Redis executes HINCRBY -1 atomically. No lock needed. No race condition. 2 concurrent checkouts for the same last unit are serialized by Redis. One sees count 1 and decrements to 0. The other sees 0 and is rejected. On cache miss, the order service reads from PostgreSQL and writes back to Redis for the next request. Full flow. Customer browses, dairy, 50 SKUs, every component is live. Here is the complete path from tab to badge. Customer taps, dairy, app sends get inventory to the API gateway. The gateway authenticates the request and routes it forward. API gateway routes to the order service. The order service is stateless. It reads everything from Redis or PostgreSQL. Any of 50 servers can handle this request. Order service fires 50 HGET calls to Redis in one pipelined round trip. Redis answers all 50 in 2 milliseconds total. Each HGET is O1. No SQL, no scan. 50 in-stock badges are ready. Array approach, 50 SQL scans. 500 milliseconds minimum, database overloaded. Hash map wins by orders of magnitude. Redis returns all 50 stock counts. Order service maps each count to in stock or out of stock. The response is ready with 0 PostgreSQL reads. Everything was in the hash map. Order service returns the inventory data to the API gateway. The gateway forwards it back to the customer's app. Customer sees 50 badges in stock or out of stock, rendered in under 2 milliseconds end to end. The entire journey, 6 hops, 1 Redis round trip, 0 SQL queries, 1 per key. That is why Zepto uses a hash map. The interview decision: use an array when you need sequential access. The key is an integer index or memory locality matters. Arrays are cache friendly. Use a hash map when you need key value lookup. The key is a string or composite and O1 access is required. The trade-offs: extra ON space, hash collision overhead, and no guaranteed ordering. For Zepto, 10,000 SKUs, string composite key, 2 millisecond budget, the hash map wins every time. Always acknowledge the space trade-off in the interview. Array is O1N, hash map is O1. Zepto stores inventory as HSET inventory. Store ID, SKU ID count in Redis, HGET on browse. HINCRBY -1 on checkout, atomic and race condition free. That is the interview answer. Next video, linked lists and LRU cache. Redis has a memory limit. When it fills up, something must be evicted. Which key? The least recently used one. LRU cache is a doubly linked list plus a hash map, both O1. Redis uses it. You need to be able to implement it from scratch in an interview. Subscribe to ByteLearn for one Zepto DSA concept per week. Under 8 minutes, interview ready. Hit the bell. See you Thursday.